interpretation of probability as modality started with Gödel, de facto with Gödel, 1933, where he wanted to interpret intuitionistic logic in terms of probability, essentially. And then he suggested axioms for probability, which are intuitively correct. And this was the system S4, in fact. And then he remarked that because of his incompleteness theorem, S4 is not sound for probability interpretation, because the principal box A implies A is, even though it is true, it is not provable. And so from there, if it were provable, you would obtain this one. And then substituting bottom for A, you would obtain box, non-box bottom, and that is the violation of incompleteness. So de facto, in order to explain this, so he indeed explicitly suggested to interpret box as probability in some probability predicate in some theory T that he dealt with. So that's essentially Gödel's idea. Then it lay dormant for some years and re-emerged in the 50s and 60s. Then there was an important work by, so there was a question suggested by Henkin concerning sentences asserting their own probability. So if phi is equivalent to box phi, what can be said about do such arithmetical sentences exist and what are they? And then Loeb answered this question. Interestingly, Kreisel first provided an answer that the answer to this question depends on the numeration, or let's say specific formula defining the probability predicate. So it could be yes and no for different formulas. And then Loeb actually gave a better answer, that if the formula satisfies so-called Hilbert-Bernays-Loeb conditions, then phi must be simply provable, so equivalent to true. So that was where these Loeb's conditions emerged. And then there comes a time when people in philosophy like Quine and his student Boulos and Montague, they started looking for a mathematical interpretation of necessity. And the first idea was that necessity is probability, and they came to the same, essentially, interpretation as Gödel. So, but for the first time, it is said that the axioms of Gödel logic, including the Loeb's axiom, appeared in the work by Tim Smiley. And this is the paper entitled On the Logical Basis of Ethics. And he dealt with, most of that paper dealt with so-called deontic interpretation of modalities. So modality is obligations. So something like box A means A is obligatory and diamond A means A is permissible. But then he had the idea of somehow relating these modalities again to knowledge. And knowledge, one model of knowledge for him was probability. And then he came back to Gödel, so he referred to Gödel in his paper and this interpretation, and said that, okay, then we have all these principles, including the formalized, including the Loeb's theorem, so to say, which was the principle of his model logic. And de facto, he stated all the necessary axioms for Gödel loop. So that was the paper by Tim Smiley.
So it came even before Lob's
After.
After.
After. So that was 55. That was 55, very early. And this was, I forgot which year it was,
Okay.
but it was beginning 60s. So I think it was something like that.
He was the first to formulate it as like a axiomatic system.
Yeah. Axiomatic system. Before that, people discussed this interpretation. They discussed conditions where de facto there were axioms for the logic. Gödel discussed it, the interpretation and some of the axioms, but he didn't know Loeb's theorem, and he didn't. So he formulated the system K4 and S4, but he didn't go to Gödel as such. So that was. So it took some years to, or rather, I would say, it took Loeb's theorem to essentially came to the eventual formulation of Gödel. But there were some other sources of this. So Tim Smiley, and then already beginning 70s, so end of 60s, beginning 70s, various people have started to systematically study this. So, and this included Bugos, and this included people in Italy, Magari, or George Bugos, Roberto Magari, and this included people in the Netherlands, so specifically de Jong. And later Smolinsky, Visser, and Van Bentelen.
Is Sambin also in the Magari's school?
Sambin, so here are a number of names. So Giovanni Sambin, Silvio Valentini, but most importantly, this was Franco Montana. And then again, somewhat later, the Russian school appeared and said, we are covering this. With a number of his students. Goryachev, for example, was one of the earliest. And then myself, and so on and so on. So, Sharokov. So these were Ignatiev. So these are the sort of first generation of students in Moscow. And then there was, so this is end of, so Artyomov started working on it at the end of 70s. So 79 was his PhD thesis. And then 80s and the end of the middle of 80s was my beginning, so to say, this area and so on. So this is, and so what I want to say is of course that this was a long development and crucial result was proved by Solovay, which was arithmetical completeness. And this solved, let's say, the great problem of this area, namely whether should there be any other axioms in Gödel logic, but for the probability logic of piano arithmetic, but for the axioms of Gödel and Solovay answered this negatively. So this is a full, complete axiomatization. So one should not look for anything more. So, in some sense, it's a negative result because, well, it's we know what we wanted to know, so to say, but it does not. So it does not tell you. Another negative aspect of this result was that Solovay theorem were very general. So they hold for any reasonable theory. And by reasonable, so in Solovey's time, so these conditions widened over the years, but basically now we know that if your theory T is, let's say, theory in the language of arithmetic and containing so-called elementary arithmetic for order to zero of x, so arithmetic was bounded induction where terms may involve exponentiation of Friedman or the exponential function arithmetic. So that's a very convenient system. It turned out to be essentially the lower bound of what we know in probability logics of fragments of Pn. But so if T contains that, T is of infinite characteristic, and this condition is a kind of soundness condition or strengthened consistency condition. So with every theory T like that, we can associate the progression, right? So during progression, T0 is T, Tn plus 1 is Tn plus consistency, Tn. And for n smaller than omega, we obtain, well, a sequence of extensions of T. If for all n, Tn is consistent, this is to say that T has infinite characteristics. Sometimes one calls it infinite height. It would be natural to call it omega consistency, but it's not what is commonly called omega consistency. So it's a weaker condition. Now, if your theory is consistent, it's not enough. It's too weak to claim that the logic will be good enough, because let's say the height of a theory or its characteristic is expressible model. So if n is the first number for which Tn is inconsistent, then this formula holds, and it is outside Gödel group. So basically, infinite height means that all these formulas for all n are so that's the condition of infinite characteristics. So it is obviously a necessary condition for the completeness of GL for this reason. But so what eventually Solovey's theorem says that if T contains A is of infinite characteristic and also of positives RE, we consider RE theories, then one can claim that the logic of the theory will be good. That's the situation. And all right. So this includes theories which are true in the standard model. So all of them have infinite characteristic. So piano arithmetic and its fragments, strong fragments, are like that. If we believe that Samuel Frankel set theory is has infinite characteristic, which we do, then its logic will also be Gödel loop. So probability logic does not distinguish proof theoretic strength. In other words, it reacts, so it detects some kind of very strong forms of unsoundness. So if your theory proves false statements and then in a strong form, then this is detectable. But basically, all reasonable theories have the same probability logic. So that's solving. And this is, of course, a theorem which is both very beautiful and has many very nice expositions. I will not present it here, but I will focus on something which is stronger than this theorem. Namely, we will deal with this polymodal probability logic. So it is denoted GLP, where P is for polymodal, has been introduced by a Georgian logician, also coming from philosophy, but he took book by Boulos, which was called Unprovability of Consistency. And this was the first book on probability logic ever written. He took to reading it, and there was a question formulated there. So Boulos introduced another kind of probability, which is currently called strong probability predicate. And namely, Boulos considered the notion which is dual to omega consistency. So if we look at so here is omega consistent. What does it mean? It means that there exists a formula phi of x such that there is an x phi of x is provable in T, and at the same time T proves phi of 0, phi of 1, or not phi of 0, not phi of 1, etc. for every specific number.
So that's if T is omega inconsistent, right?
Right, omega inconsistent. Right, this is omega inconsistency, and omega consistency is if these two conditions simultaneously do not occur. You can also, yes, and the notion of omega inconsistency and omega consistency can be formalized in arithmetic as well, because you can just say that there exists a formula phi, so something like that. There exists a formula phi, I write it like Gödel number, such that it is provable in T that it's phi of x, and for each n it is provable T that not phi of n bar. Right, so that's essentially the way this statement can be formalized in the language of PA itself. And dual for consistency is the notion of probability. So if instead you now consider the formula that not phi is inconsistent, this will be another arithmetical predicate which behaves like probability. So it is, in fact, a probability from the axioms of your theory T and unnested applications of omega rule. So you allow one application of omega rule, and that's this notion of probability. So, and Boulos showed that the logic of this will be Boulos, the logic logic of omega probability. The notion of dual to omega consistency. So this was proved essentially by the same method as Solvay construction, but let's say modification was that now your proof predicate is not sigma 1. So this theory is not, omega probability is not sigma 1, not sigma 1.
Sorry, could you explain again what is the omega probability predicate?
It is written here. So we say that the formula phi is the formula phi is omega provable if its negation is omega inconsistent. So essentially, we consider formulas proved by one application of omega rule, the axioms of T, and close this and deductively close this set of formulas. That's your notion of probability. So using this mechanism, for example, you can prove every true pi 0 1 sentence. Why? Because if your sentence is pi 0 1, then it has form for all x phi of x, and with phi primitive recursive or bounded, and then for every specific n, you can prove this primitive recursive or bounded formula. And using application of omega rule, you infer for all x phi of x. Well, that will be already gives you all true pi 1 formulas, pi 1 sentences, as omega provable.
Yeah, I think your definition actually misses something, because I think you have a basic condition of what phi is, but phi should be a premise, I guess. So if you, because you want it also talk about like what you are proving, if you want to provide the probability predicate.
Yeah. So what is that? So
now it's certain.
So we need to deductively close all the set of omega.
I guess it's
omega inconsistent for, as I said, but not.
right.
Right.
So I guess,
So we consider the deductive closure of the set of all omega.
I mean, also I guess the question: do you allow like one premise like this? Do you allow like any finite number of premises? Yeah, probably it doesn't matter.
I think it doesn't matter. So you can reduce finitely many to one, and
Sure.
So this is anyway. As Smolinsky wrote in his textbook, or even in the survey paper, the notion of omega consistency has a historical value, but it is not the most natural from any point of view. And he suggested a different probability predicate, namely the probability from all true pi 1 sentences. And this happened to be another form of strong probability predicate for which one can prove analogous result. But anyway, so Bullis proved that Gödel-Loeb, so this omega probability predicate, when properly formulated, has the same logic of Gödel and Loeb. But then he asked the question, what will happen if we consider both omega probability and ordinary probability simultaneously in your language? And that was a question that Japaridze, in fact, tackled and managed to answer. So 1986. And moreover, he introduced even next stages of this omega probability predicate. So if you nest your omega rules twice, 3 times, and so on, you obtain a sequence of stronger and stronger, let's say, probability predicates, which will be, in fact, the complexity of these omega probability predicates R sigma 2n. So that's a very strange complexity measure, if you like, but that's so it happens. If you close under omega rule twice, you will be able to prove all through sigma 4 sentences and so on and so on. So that's the interpretation that Jaquaritis dealt with. So Jaquaritis' work was a big step forward. So it was the first, I would say, historically genuine modification or expansion of Soloway construction by some non-trivial means. So the results before that were sort of just applying the same construction that Soloway invented in various particular cases or situations. But Jaquaritis had this significant advance. So it was complicated. It was written in his candidate dissertation, never published in any serious journal. But Bullis learned about it. So Bullis knew it, and of course he was highly excited about this result because it answered his long-standing question. And later Ignatiev actually read this Jaquaritis' work and simplified Jaquaritis' proof, kind of clarified the whole situation with GLP, and proved a number of interesting properties of that system, like a fixed point theorem, Craig interpolation theorem, and so on and so on. So, but then later, already, so the work of Ignatiev was in 1993, and this topic lay dormant for quite some time, because at that time the focus of all the people working in this area was on this arithmetical completeness results, and it was not at all clear why we should focus on such non-RE theories. So people were looking for polymodal probability logics for RE theories like piano and ZF, or maybe some other pairs or other kinds of theories. There were results about logic of interpretability beginning at that time. So the Jaquaritis logic did not appear to be very, let's say, promising. So it was kind of no applications were inside. But then applications came through the study of progressions of reflection principles. And then there was this renewed interest toward this system, GLP, and people started to sort of explore its properties in much bigger detail, and so on and so on. So there appears a series of papers on GLP and how it behaves, what are its models, topological. So by now it is a very well studied system. But the goal of today's lectures, or 2 lectures, is to sort of go into the basic arithmetical completeness result. And of course, the proof comes from my paper, which is called A Simplified Proof of Arithmetical Completeness, 2011. And of course, it is further simplification of Ignatiev's proof of Jaquaritis' theorem. But basic idea are of course Jaquaritis. So here is that's what we see here. So let us formulate the axioms of the model before going into the details of interpretations and instructions. So what are GLP? The usual model logic, where modalities are traditionally denoted like n in square brackets, because in those times producing indices was not very in typewriting was not very nice. And also Japaridze wrote there was like box with n inside. This is even harder. So this is the nth modality corresponding to the nth probability predicate in that sequence. So the 0 is just the ordinary box, and for us it will be essentially the probability predicate for t. So that's and the further boxes can be selected differently, as we will see, but primary interpretations are like the Japaridze or Ignatius. So the axioms. So the axioms, part one, they're essentially the axioms of Gödel-Love for every n, but let me write them down here. So we have something like normality, axiom K, sometimes denoted. So second axiom is the Love's axiom. There are two infinite rules, and this is the modus ponens rule and the rule of necessitation. We can also formulate it like this. But the interesting principles are relating different boxes, and these are the principle like box n, or let's say box m phi implies box n phi or n. So self-explaining principle, and more interesting principle is this: not box m phi implies box n, not or then yeah. So these are the two additional principles. So this one says that the theories increase in strength. So there is inclusion, and this in fact tells you that the gap between n and m is very strong, very big, because recall that no reasonable theory by Gödel's incompleteness can prove unprobability of anything, because unprobability of anything implies consistency. So we do not expect that m, not m phi, holds. In fact, this formula will imply box m bottom by the even say equivalent to that. So, however, if we replace this m by n, and this is no longer the case, and we see that if this formula not box m phi is true, then it is n proved. So, in some sense, it says that the theory n proves a good number of true statements, namely all those of the form not box m phi. It's instructive to look at the case where, let's say, n is 1 and m is 0. So if m is 0, then this is just the ordinary probability box PA. And not box m phi means that, okay, phi is not provable. So this is by one statement, not provable something. Moreover, let's say there is a theorem which is reminiscent of jump inversion theorem in recursion theory, which is called Friedman-Harrington-Goldfarb theorem, that said that essentially any pi1 statement above consistent, stronger than consistency, can be represented in the form of unprobability of something. So by claiming hypothesis like this, we de facto are saying that something like every true pi1 sentence of a specific kind, but nevertheless, every true pi1 sentence must be provable, must be one provable. So that's essentially the difference in strength between 1 and 0. So that's but if you consider 1 instead of 0, then here you will have already pi2 sentences, and 2 probability will be proving arbitrary true pi2 sentences, and so on and so on. So this keeps increasing in strength. So that's why these axioms hold, and that's why these principles hold for these strong probability. So if we just interpret box 1 as probability in P arithmetic plus all true pi1 sentences, clearly this one will be valid. It takes some time to prove Loeb's theorem, but I will just remark at this point that this proof is, even though it is for box n, it follows essentially the same pattern as the ordinary proof of Loeb's theorem. So it's not any different in, you just consider the fixed point, appropriate fixed point for box n, you get it. So that's essentially the kind of soundness you get. Right. So this is GLP, and a little bit more about formal details, since we are interested not only in soundness but in completeness. So let's specify for what kind of sequences of probability predicates we will be talking about. So we say that so let's consider an arithmetical formula, some arithmetical formula, which I denote proof X. And we say that this formula is of level n, so probability predicate of level n, if the following conditions. This formula proof is sigma n plus 1. Is sigma n plus 1. Well, then a theory is some theory like P average. So proof is a sigma n plus 1 formula. And secondly, proof satisfies in T the first two conditions, the first two conditions. In other words, this one and this one. If T equals 5, and then T equals proof of 5, and T equals 5. Sorry. Right. Something like that. So that's and the third condition, it would be nice to say that we just require that it satisfies the third loop condition, namely its transitivity, axiom box implies box. But here we need slightly more, so we just say that it is sigma n plus 1 complete. The proof is provably sigma n plus 1 complete. In other words, T proves that, so if P is sigma n plus 1 sentence, then T proves phi implies that it is proved. Right. So that's what we require of probability predicates of level n. If n is 0, then we obtain the usual. Then clearly the usual probability predicate is a probability predicate of level 0 because it's sigma 1, it's sigma 1 complete, and it satisfies both all these conditions. But if you add all true by one sentence, then you obtain more. So we have this. Let us just for the record. So I'm using these Greek letters as a new sort of variables ranging over Gödel numbers or formulas in arithmetic. So just to save some space, there is a beta segment. Beta is a true by n sentence, and the arithmetic rules beta implies right like that. So something like that. So we can say within the language of arithmetic that alpha is n provable if there is some pi n sentence beta which is true, and P arithmetic plus beta implies something like that. So that's clearly a sequence of probability predicates, and it does. You can verify that it does satisfy all these properties. For example, if you want to verify axiom 1, what will you need to do? So you need to formalize a certain argument within piano arithmetic. So you assume that phi implies psi is n provable, which means that there is a beta 1 which is true, and beta 1 implies phi implies psi. And then this condition gives you that phi is n provable. So it means that there is a beta 2 such that beta 2 implies phi. And beta 2 is also true. So you have this beta 1 and beta 2, and you know that both of them are true pi n sentences, so you can consider their conjunction. And then, by the properties of truth predicate that you assume to be formalizable in PA, beta 1 and beta 2 will be also true pi n sentence. And of course, it implies both pi implies psi and phi, so it implies psi. So this argument is clearly formalizable in piano. So which shows item 1. So as for item 2, as I mentioned, so here one must apply simply the first, so loops for proof n. So you consider psi, which is how do you prove the box n proof n of not well, the fixed point for up. So mm, right. Psi implies phi, something like that. Or sometimes one writes something like that. So right. So if phi is positive, then this will become the usual Gödel when psi is equivalent to not provable psi. Psi is certainly so not probability. And if phi is some arbitrary sentence, then you consider this fixed point. So, and reasoning from psi, from Loeb's conditions that you already have, including sigma incompleteness. So, and by the way, of course, this sigma n plus 1 completeness, it implies the familiar principle that box n y applies box n phi, right? Because sigma n plus 1 and box n is sigma n plus 1. So that's a specific sigma n plus 1 sentence for which you assert completeness. So, then you have all three Loeb's conditions, and then the Loeb's theorem goes through without any change. So that's basically the
Yeah, I think this point is not wrong.
yeah.
So I think it should be psi implies 5 side of probability. No,
It doesn't matter. Both of them work. Right.
okay. No, I don't know. Yeah.
Exercise.
Okay.
Exercise. But it is well known that both versions work. So,
Okay. Okay. Yeah.
okay. Good. So these are so this is the setup. And as I said, so we call okay, so let me. So another example of a suitable sequence of probability predicates is formalization of this omega rule. Algebraic that we will not go into it, but it will also yield another sequence. But already of levels 2n. Right, so here we have for every level a suitable probability predicate, and there we will have at even levels. The probability predicates, the logic will not be affected by this. So what we would like to say is that so there is this, we say that okay, let's call it denote it. I denote sequences of probability. Okay. Yeah, sequence definition. So y is a strong sequence of probability predicates for over t over t if these numbers R0, R1, R2, increasing sequence of natural numbers such that predicate n's predicate is probability predicate of level Rn. And of course, they provably increase. So the key point is that they should really provably increase in T. So T should know that n plus first predicate is much strong, contains the n supreme. Something like this. But for our canonical sequence, when we add by two sentences, since we know that every by one sentence is a by two sentence, so this is kind of a triviality. So we trivial. All right, so that's a strong sequence of probability predicates. And the theorem, so for every strong sequence, of probability predicates, I over theory T, and here we unfortunately have to say that T contains arithmetic rather than elementary arithmetic. We don't know if result holds for elementary arithmetic. That's an open question. So, so soundness holds for elementary, but completeness is an open question. We can discuss it later. But for every strong sequence of over A, yeah, DLP, and yeah, such that oral and probability is sound, proves only true in the standard model. Sentence is true in the standard model. GLP is arithmetically complete. And to be more, let's say, specific about what it means to be arithmetically complete, so we define, as always, we define this arithmetical interpretations or realizations. So the function f from propositional variables to sentences in the theory is called a realization. If well, let's say from formulas, from formulas to sentence is called a realization if the following condition must be satisfied. So if f associated with pi, right? So f pi respects propositional connectives. So it's translation of modal formulas into arithmetical formulas respecting propositional connectives. And it translates the and probability as the formula itself. So we just translate box n as probability number n in the sequence pi. So this is the realization or right. So this is a function f pi, so given pi, so pi is fixed, and then we consider arbitrary maps from formulas to sentences satisfying this condition. Essentially, it means that we assign arithmetical sentences to variables arbitrarily and then extend them by these rules to arbitrary formats. And then arithmetical completeness means that if GLP, or essentially GLP, if it does not prove phi, then there is an F such that for every pi, then there is an F such that the arithmetic or T does not prove F of phi. So this is the completeness part, and the part that GLP proves phi implies for all F proves F pi of phi. This is the soundness, arithmetical soundness part, which I have already explained. So for every strong sequence, whatever the interpretation of variables, interpretation of the formula will always be provable in T. So the key point is, let's say, the substance of this theorem is to show this completeness, arithmetical completeness. Right. So that's this is more or less what is claimed here.
Excuse me, can you hear me? Yeah, on Zoom. So, can you hear me or not?
Yes, I can hear you. Yes.
Yes, could you please repeat the condition one in the definition of strong probability predicate, because in Zoom we cannot distinguish this, the pictures.
Condition one.
Да, yes.
So the condition one is stating that the level of the probability predicate number n is this Rn. So the sequence pi is a sequence of probability predicates of levels R0, R1, R2, etc. So that's more or less what condition one says. And condition two says that they're provably included.
Yes, thank you, I see.
Okay.
Sorry, is the point?
So that's the statement. So maybe we should discuss.
Okay.
So going into the proof, I will outline the outline or general scheme of the proof, and the substance of the proof will be next time. So outline of such proofs, they all follow the same principle. So firstly, step one. To show that if phi is not provable in GLP, then there exists a Kripke model W such that W in some world else falsifies our formula phi. So typically also in this case, we can assume that this model is finite, although construction works sometimes also for infinite models. Here it will be finite. Of course, it needs to be specified what kind of model we need here so that we do not lose information. And not losing information in this step means that we have so-called completeness theorem for Kripke semantics. Unfortunately, GLP is not complete for Kripke semantics, for Kripke frames, let's say. And semantics for it is is a complicated issue. However, as it happens, we can produce here a certain surrogate model, which let's say for a specific formula phi, we do produce a specific model with additional properties, technical properties that will allow us to do the next step, not to lose all the information and to do the next step. And step 2 is Soloway style construction, embedding W in dA. Now, what it means to embed here, essentially, in practice, we will see that we will associate with worlds in this Kripke model specific arithmetical sentences constructed by diagonalization. It's a tricky part is to devise this diagonalization and see how it why and how it works. On a more general, let's say if we let's say step down from concrete construction here and think about how Soloway could have come to this idea. So basically, we should recall the following: that if we look algebraically at it, then we are constructing certain sentences which are elements of the Lindenbaum algebra of arithmetic. And this embedding, in fact, induces, essentially it provides us with a sub-algebra of that algebra. So we, de facto, what we are going to do, we are going to, so with the Kripke model, you can also associate the algebra of all subsets of that Kripke model with the Boolean operations corresponding to Boolean connectives and with modalities corresponding to these operations on subsets. And this Kripke structure algebra will be embedded into the Kripke, into the algebra, into the Lindenbaum algebra of arithmetic, together with all these operations. And our task is to ensure that this is a proper embedding, that nothing is, that is indeed an embedding, because essentially what we see here is that if phi is not 1 in the original algebra, so if phi is not provable in GLP, then in that model, the phi will be false at a certain point. So there is a point where phi is false. That means that interpretation of phi is not 1 in this algebra, and it should go to some element in the Lindenbaum algebra, which is not 1, right? Unprovable in T means that it is not 1. So that's essentially the embedding of this.
I think it's morally true, but I think it's. I don't think it's exactly true. I think embedding is actually going into factor algebra, not Lindenbaum. So it's okay.
Okay.
Yeah, it's kind of it doesn't matter, but more like
right.
I mean, that's the reason so the point of me, of course, is because of the height, right? Because real algebra has infinite height. And this should be preserved by some algebras.
Right. You are quite right. So,
Sorry, will this be sort of an, can you hear me?
Once again?
Yeah, sorry, I was just going to say, will this be essentially like an embedding up to some number of modalities and up to so essentially it's sort of taking a collection of modalities and saying
Right.
I'll preserve exactly these ones but not them in general, which is what typically
Right.
happens when you're trying to
when
prove this
going
sort of
from, let's say, free GLP algebra into a finite Kripke model, what we will get, we are essentially considering a certain factor algebra.
yeah, it's essentially sort of a filtration
And it will be a
as we
finite thing. And then we will indeed right. Still in this factor, in this finite factor algebra, our element that we did not want to be one in the original algebra, it still will not be one. And then it will be isomorphically embedded into a certain factor algebra of the Lindenbaum algebra of Riff. So that's the proper way of doing it. However, let me say that in fact there are these uniform versions of completeness theorem, which are saying precisely that the free algebra is simply embeddable into the algebra of arithmetic. So you can in fact define by slightly more elaborate construction, but not principally the real embedding of the free GLP algebra into the algebra of arithmetic. So that's the so-called uniform version of Soloway theorem. Right. Usually it is done by considering the collection of all possible finite structures and embedding them simultaneously into PA by one specific realization. So that's more or less the idea. Right. Yes. So next time, what we will be doing, I will probably skip this model part because it is very standard. I will specify exactly what kind of structure we will obtain here. There will be a certain well-behaved approximation to GLP, called the system J for Japaribza. So we will, in some sense, from the unprobability of phi in GLP, we will infer that there is a certain model of that logic J, which falsifies phi, satisfying additional requirements. And then we will focus on this specific arithmetical embedding construction for this modification of Soloway construction. And of course, a particular, since all these modalities, they include the usual probability predicate for PA at level 0, so to say, if we would like to consider such a sequence, you will see a consequence will be the ordinary Soloway theorem. So Soloway theorem, the original one, the famous one, is less let's say, consequence of what we will going to prove. So I exposed you, I'm going to expose you very unpedagogically to the more complicated construction rather than to the easier version of that construction first. But the advantage is that the easier version is in Bulos and Samarinsky books. You can read it there. So it's also in various survey papers and it is well understood. But for GLP, it's the first sort of step into the more complicated, let's say, modifications of Soloway. So that's it. So I guess for today, it's time for us to finish. So let's finish with this. And I would like to say for those who are in Zoom that we will probably change the day of these lectures. It will be on Tuesday
At 1 p.m.
at 1 p.m. Central European time.
Yeah.
So
Ну, один посмотрим.
other parts of the world it could be slightly later. But Tuesday is will be the day. So next Tuesday, I hope to see you next Tuesday.
Yes, it would be great. Thank you.
Okay. Okay. Mhm. Yeah, thank you very much, and yeah, goodbye. So let's stop.
Yeah, Oscar, okay.
I can, maybe Oscar, you can stop the recording, please.
So it is.
I don't know.
That's, yeah.
Let me.
Okay, thank you very much again. Bye.
The right.
So there were some
Thanks so much. Bye.
questions or something in chat. Okay, that was before we. Okay, so stop the record. Maybe the recording has already been stopped.
That's red button above.
Yeah, sure, yes. Yeah. Stop.
Okay.